start evaluating exponential function base E. Now, E, before we get started, is it's an irrational number. It's kind of like pi, okay? Fact is, it shares a key on your calculators, which you might as well get out now because we will be using them today, okay? But E is an irrational number that just keeps on going forever. Never stops, just like pi does. Except it's where pi is used in circles and arcs, E is used in doing basically predictions and financial work, growth rates, decline rates. If a city's population is going so much, what are you expected to be in 25 years? So what buildings, facilities, water plants, sewer plants do you need to build? Likewise for schools. So anyway, we'll be talking about E, and then we're going to do a couple of other things as well. Okay, here's just what I just said. Okay, now, if you're interested, the way they derived the value of E is by this exponential function. Do I expect you to know that? Heck no. All I expect you to know is that E is approximately that. Okay, you need to memorize this much of it. And we have to use the approximately symbol because that is a rounded off value. Anytime you use a rounded value, you must use approximate instead of equal. Now, notice this is almost 3. It's 2 3/4, right? About. So what that has implications is if we had a graph of 3 to the x, then e to the x is going to be real close. Just slightly flatter in terms of how sharply it goes up, okay? So that's just kind of an estimation sort of a thing, also graphing. Now, oh, they want you to round this thing to 4 decimals. That was the original problem on here, and they want you to round this. Well, the answer then is 2.7181. Let me go back to this slide. Okay, 3. Okay, so that would be rounded to 4 places. You know, the 5 and up rule. No big deal. Okay, now, how do you find E on your calculator? To get E, it's right here, this little button down at the bottom. But to access the E part of that button, you have to hit alpha. To access the pi, you have to hit shift. Okay? It's kind of a left, right sort of a thing. So that gives you your specialty functions. Now, in this particular case, I'm going to take that, that's how I get E. Now, if I wanted E to a power, some power, I don't know what power, just some power for right now, then I use, after I type in E, then I'll hit the x to the whatever power compared to the x squared power. That one will just make the x squared. This one will let you choose any power, even negative ones. Okay? So that would be the next thing that you would do. Then, in this case, I have a 2 that I typed in there in the box. Okay? And then I hit the equal key. So you get E squared is this. Okay. Now, if I want to round this to 4 places, 1, 2, 3, 4, I've got a 0, but behind is a 5. So I'm going to have 7.3891 would be my value there. Okay. But the main thing I'm doing here is showing you how to access stuff on this. That's what I'm really doing here. Okay, any questions on this before we go on?
I just did, there's one that says IN under the law something. I said that one.
Which one? Show me. Which one did you get? Okay, well, we'll get, in some cases,
Okay.
not every case. There are times when what her question was she hit this natural log key. Okay, natural log, I'll explain this very briefly right now, but we'll go into more detail on this later. I'm just going to choose right here as a space to write. Natural log ln is the same thing as log base e of, let's put an x behind that, let's put an x behind this. Those two are equivalent statements. So this pulls up an e, but it isn't necessarily the e key in its own self. Okay. I hope that explains that well enough. Okay, let's go on. Now, find the square root, find e squared. Well, we just did that. Now, do e to the -3. I just happen to have a calculator. Alpha, e, whatever power, -3 equals. Okay. So in this case, 0.0497 approximately. Why did they go up to 8? Because this 8's 5 and up. What I did initially is just read the numbers. Bad on me. Okay, let's look at the next one. This next one's kind of interesting. So let's put the e in there and the power key. Now the whatever square root key and the 7 equals. And there's what you get. You can see how easy these Casios are to use. And what you see is what you get. You enter it just like if you were writing it on a piece of paper. Okay, e to the pi. There's got to be some kind of a math joke that ought to be able to come out of that. E to the pi almost sounds like eat the pie. Oh well, I'm trying too hard. I'm not even getting any groans on that. Okay, to the unknown power. Now I go to the alpha key and hit that. And I put pi in there and equals, and that's the value I've got. Fairly simple to use, as you see. Now, let's go to this page. I'll just leave, let me clear this out. You actually don't need a calculator to do this page. Okay? Well, actually, you kind of do. Because the numbers get complicated as you go. Now then, what we're dealing with here, this orange is the e to the x curve. Now, any exponential curve is basically going to go through the point 0, 1. That's going to be kind of your anchor point on all exponentials, unless there is a modifier. So for the e to the x curve, if we added a column down here, what was e to the x? Well, if x is 0, what's anything to the 0 power? 1. Okay, so if e to the 0 is going to be 1. What is pi to the 0? 1. That's why every exponential curve, unless it has a modifier that shifts it left or right, up or down, is going to go through that point 0, 1. Okay. Now then, we can do all of these calculations. E to the first is 2.718. Well, you're not going to graph any more accurate than a tenth, and probably even not that much. You're going to say that's about 3/4 of the way. So if x is 1, then we're up here not quite up. This is not perfectly accurate. It actually should be about where my fingertip is. Okay, then e to the second. Well, probably need the calculator there. We did that one a few minutes ago. It was 3.8 something, something, something. Okay. Excuse me, 7.4 something. And so if x is 2, then we're up here about 7.5, real close. And if e is 3, then we get this 20 way up here off my graph. Well, let's do some negative values. Well, if it's -1, okay, you still get a 1. If it's here, you get 1. Notice this scale is by 2s. So right there, 1. Okay, now here, if it's -1, if it's 0, it's still 1, just like before. If it's -1, it's about a half. We're on this one now. Here. Okay. Then if it's -2, it's getting closer. And if it's -3, it's getting closer and closer and closer, but never quite crosses the x-axis. Okay. That's a boundary on that thing. Okay. Called the horizontal asymptote. Now, what am I doing? Oh, these are. Why is this affecting that? Oh, I've got this turned off. It's not in presentation mode anymore. Okay, so I need to go to this. Explain how this graph is related to that graph. Okay, here is our basic e to the x going through the point 0, 1. And then it's similar to a 3 to the x graph. 3 to the x would go through this same point. Then if you have if you had 3 to the x, if x is 0, you'd have the point 0, 1, or a y value of 1. If you have 3 to the first, then you would have the point 1, 3. Okay, so here is 1, 1, 2, 3. If you have 3 to the second, you're going to have 2, 9. Okay, whoops, that isn't the 3. Here's 3 right here. Here's 3. 1, 2, 3. I quit paying attention that my scale was by 2s. So 2, 9. So actually it would be here. Yeah. Okay, so now if x is, and my x scale is by 1s, so I don't have the same vertical and horizontal scale here. So if x is 2, then I've got 2, 4, 6, 8, 9 right there. And then I would have 27 way up, and you see here is the 3 to the x graph. Now, the reason that I'm showing you that is so that you will remember that 3 to the x is very close to e to the x. They're very similar. The 3 to the x is just slightly steeper. Okay? Now, I'm going to get rid of that. I'm just giving you that for reference. So now let's address this problem. If I start with this equation, what would that cause me to end up with? I'm going to do it in steps. First, you deal with this. Technically, there could, I'll put the x back in there. There could be a parentheses around that. What happens when you have a number contained with the variable? It shifts it left or right opposite of sign, right? If it's contained under a radical, if it's contained in an absolute value, or if it's contained in a parentheses, shifts it left or right if it's with x. Opposite of sign. So that means this negative means we're going to shift to the right one place. So every point on this is shifting to the left or to the right one place. Okay? So it shifts to the right one space. This negative in front, if you remember from when we were doing reflections, flips it up from top to bottom across the x-axis. Okay? So that changes positive y's to negative y's, and negative y's to positive y's also. So then we take these points on this modified one, and we flip their y values and bring them down here. Like so. Okay. So this is our final graph of that. And that's how it compares to this. Now, the reason that I'm telling you this is so that you don't have to put a whole bunch of x values in right here and do an XY table, even though you've got a calculator. The way I did it is vastly faster than making an XY table and plug in all those values. Now you could, okay? Let's put in that equation. Minus alpha E to the power of, and I have to use in this calculator a parentheses on it. Okay, now I'm going to start with 0. What is it? Plus? No, it's minus 1, and close up the parentheses, and I can hit an equal sign. In other words, roughly negative 1/3 is the y value. Now then, how do I find the next one if I'm making an XY table? Well, I use this backup key until I get just in front of that 0. I delete the 0 and I put in a 1. And then I hit the equal sign. And we got -1. Okay? 1, -1. And then I back up again. You see why I'm just showing you this backup trick so you don't have to re-enter everything every time? So let's put a 2 in there. Equals, okay, over 2, 1, 2, and down about, actually 2 3/4. Okay, so my graph is off just a little bit, not quite steep enough. Anyway, you see how much easier we did it before than doing all this entry for each value. Okay. Question? Okay. Now, compound interest. This is something that will be on the final most likely. Has been virtually every year. There are 3 types of interest. There's simple interest, which often auto dealerships say, hey, we offer simple interest. What that means is if you have a 5-year loan, they take how much you borrowed at whatever interest rate they're going to try to give you, depending on your credit rating. And then they're going to take it times the full 5 years. They're going to take the amount you borrow at whatever interest times the full 5 years, and that'll tell how much interest you have to pay in addition to what you borrowed. And then they divide it by 60 months. 60 months is 5 years. Figure out what your payments are very easily with that formula when you go into a car dealership, except don't forget the property tax and all of that. If you include that in the loan, that's going to jack it up even more. Okay? So that's simple interest. This is compound interest. Let me get rid of this stuff. This is compound according to what they call periods. How often a year? Okay. If they call it semi-annual, then that would mean they're going to calculate the interest twice a year instead of once a year. And then they're going to add that interest on, which is going to make the accrued amount bigger. Now, you use this mostly when you are in savings. Okay. In other words, it adds interest on interest. This is no longer the interest, but this is the original principal plus the added interest. And in this formula, you have the 1 plus the interest rate over how many times a year you do it times to the power of how many times you do it a year times how many years. Okay, now, if they tell you that they're doing daily compounding, that means they're going to do it 365 times a year. Okay, and you would have a 365 here and a 365 there. If they tell you you're doing it quarterly, then you're going to have a quarterly is a fourth of a year. So then you're going to have 0.25 here and here. You could use the fraction, but that'd make it a lot more complicated, because then you'd have compound fractions. What if they had said 9 months? Now that's a weird number they'll never use, but what if? Well, 9 months is what part of a year? 3/4 of a year, or 0.75 would be your interval in that case. And then finally, we have what we call continuous or infinite interest calculations. Okay, and here's where E comes in. Okay, here's where that never-ending decimal comes in. So we take the amount you borrowed times E to whatever the interest rate is, times however many years you want to borrow it. That'll tell you the total amount you have to pay back. Or if it's a savings account, how much you'll have in your savings account after so many years. And it does make a difference. Okay, this one will earn you more money than this one will with 365 compounding. It'll be a slight difference. Now, in some years on the final, we've had a question. It gave you the principal, it gave you the rate, it gave you the number of years, and it told you how it was calculated, whether it was continuous or whether it was compounded at some rate. Okay? And in that problem, it can make a few cents difference between 365 times a year compared to continuous. Guess what? On that question, if you choose the wrong of those two formulas, the most points you can get is 1. Or if you choose the right one, of course, you can get possibly a 4 if you do it all the calculations correct. Okay. So you do need to memorize all 3 of these formulas. Okay, let's look at this one. 15,000 is invested. That's your P. That's your starting amount. Okay. 2.5% interest. We have to convert it to a decimal to do calculations. Move this decimal over 2 places to the right. Or 2 places to the left, rather. Okay, and then they want it to be 7 years. We're going to do this thing for all 3 kinds of, well, actually, I don't think we're going to do simple. Compounded annually. What does annually mean? That means you're going to compound it once a year. N is 1. That's different than compound daily. And you'll get a different number. Okay? So anyway, these pieces of information in here, 15,000 times 1 plus 0.025 to the 7th power. Does anyone want me to put that in my calculator? Because that's the way you're going to do this problem. You're going to work this problem, but you're going to write this down first so I know what you're putting in your calculator so I can give partial credit. Okay? While you're using your calculator on these problems in the next bunch, if you put it in the calculator, you put it on the paper. Okay? And we get this value out when we put it in the calculator. Remember this number just for a few moments, not forever. Okay, anyone not ready to go yet? Okay, now we're going to compound quarterly instead of annually. That's 4 times as often. Okay, and this is an investment, so this is something that earns you money. So it's important to you. Well, in this case, we still use the same formula. We put in the 15,000, we put the 1 plus the rate over 4 times a year. And because this is the times years, we could put 4 times 7 up here, but you might as well just put 28. And you got that 28 from 4 times 7 years. These two multiply together. And it comes out this much. You have made about 20 bucks more than you did the first way, didn't you? If you compare your first one we had on the previous screen. Okay, what if it's compounded continuously? Now we're using the E formula. Okay. Accrued amount equals. So we put in the 15,000, we key in the E, we key in, this time we have to use the parentheses when we put that times in there. Okay, in our calculator, and I am going to do this one on my calculator. And you still get even more money. An extra 10 bucks over the quarterly and an extra 35 over the annual. Okay, let's put this last one in here. 15000 parentheses are times E. So alpha E to the power of, and I'm going to put in my parentheses 0.025 the interest rate times 7 years, close up the parentheses, and I can hit the equal sign. Remember, if it's money, you got to round it off to 2 places, which some of you forgot on the last question on the last test, where the answer was $16.80. Some of you left off the 0. Bad on you. Okay, questions on this? All right. Oh, by the way, when it comes to money, and if it's a loan especially, if there is any leftover remaining digits, a bank will always round up how much you owe. I mean, even if it's like 0.821, they'll round it to 82 cents or 83 cents, I mean. And so do stores, for that matter. Rid of that, and we'll go on. Now, here we go. If you borrow 12,000 at 5% for 6 years, find the amount owed if you're charged simple interest. You do that. You do that. I equals PRT. I is Curti. I saw a couple of smiles at that one instead of groans. Just spelling it out phonetically. Well, let's do that. Simple interest. 12,000 times the rate. What did we say? 5%, 0.05 times the time was 6 years equals. You're going to pay $3,600 in interest. That means instead of paying back 12,000, you got to pay back 15,600. This is like a car loan. That's the way a car loan works. And then you would take that 15,600, 12,000 plus this, and divide it by 60 if you borrowed it from 5, or divide it by 36 if you borrowed it for 3 years. Okay, well, in this case, they said 6 years. So you'd have to divide it by 72. 72 months in 6 years. Okay, let's go to the next one. Quarterly. So in this case, I've got the 12,000 again. Parentheses, 1 plus fraction 0.05. Go down to the basement, 4. Get out of there. Close up the parentheses to the power of RT, or NT rather. In this case, 4 times 6 years is 24. I'm just going to type in 24. Equals. That's how much you owe then that you have to pay back. Okay. Well, let's go to the next one. Hopefully you're doing this too. I shouldn't have thrown that out. Oh, daily, 0, 0, 0, parentheses, 1 plus fraction, 0.05, go down to the basement, 365. Get out of that. Close up the parentheses. Go to the power of, in this case, I'm going to put in 365 times, how many years? 6. 6. Close the parentheses, equals. Saved me a little bit of money, didn't it? Okay. Saved me a little bit of money. Remember, it's simple interest. You ended up paying back 16,600, which is the way car dealerships do it. Okay, now let's go to the continuous. Okay, so I'll clear this out. 12,000 whoops. And times E to the power of 6 and the interest rate first. What in the heck did I do here? I don't know what I did. I hit a wrong key somewhere. Let's start that over. 12,000 times E to the power of parentheses. Okay, the interest rate 0.05 times 6 years, close it up, equals. Now, this time is only a matter of very little difference between doing it daily and doing it this way. But it did save just a little bit more, okay? Now, you buy a house someday. Hopefully that's in all of your futures, okay? Bank's going to charge it probably continuously, okay? That's why if you make 2 payments a month instead of 1, it goes down faster because that P keeps getting smaller, faster. Okay, just a little word of advice. Okay, here, problem, okay, for these, for question A, here's what you would use for annually, B, monthly, okay, or C rather, monthly, E, continuously, well, here's daily, and then quarterly is up here, and then continuous is down here. How you would set it up, okay? And we're not going to do those because it's just repetitive what we've been doing. Okay, use exponential functions in applications. Okay. Estimate of population is 111 million. Okay, they're just not stringing on the 6 extra zeros. They're working this in millions. Okay, knowing that there's 6 extra zeros behind that. Now, what is this? This is the number derived from that. Okay. The 0.9994 and T, and in this case, they're using a 1 as the number of times that is calculated. Okay, or annually. Why did they use a 1 for annually? There's a hidden word in here that tells you that. Per year. That means annually. Okay, you got to watch out for the subtleties of the language on this. So anyway, that's why we have a fraction here, is because it'd be a 1 under that. Okay, now, where T is the time of year since 2010. Well, what would we use for T if it were 2010? Well, right now we'd use 13 years, right? So let's put this in here. 111 parentheses 1.00994. What they've done is they've added this 1 and the 0.00994 together. Because that's over 1, we put in the parentheses and we take to the power of, in our case, 13 years. That means this year, the population should be 126 million. Is what that calculation means. And a little over. Okay, 126.25 million in rough numbers. Okay. Now, is that absolutely accurate? No. It assumes that it's a continuous, steady rate of increase. Okay, something to do with birth rates and things like that. The United States is going to have a huge differential in the next few years. The annual birth rate in 1921 in the US was 3.3 million babies live born. That's how much our population conceivably would increase each year if you don't kill off some people, the old folks like me. Okay, so assuming that we just had that growth rate without any deaths, we've had 8 million immigrants come into the United States in the last 2 years. More than at least 2 years of our birth rate. So we're going to have a population explosion that's going to be coming in the near future. What effect does that have on services? What effect does that have on classrooms and teachers for schools to support them? All of these things make a difference, okay? Now, I'm not talking any politics. I haven't said against or for that. I'm just saying what happens, and it's mathematical. Okay, well, here we go. This one. This is a function of time, 4 years. Okay, that's what that notation means. Okay, here's our time exponent. They chose the time to be 4 years rather than 13 that we did. Okay, so it does make a difference. What about 75? See, here in 4 years, they're at 116 or 115. Look how big they're going to be 75 years from 2010. It's going to be huge unless there is something significant that affects their population. COVID was a significant effect because it killed so many people. Now, this is going to seem strange for me to say, being the age that I am, the vast majority of the people it killed off were old folks like me, which means we're not going to be probably reproducing. Okay? And affecting the birth rate. So in that sense, it doesn't hurt, but it does make a difference in the end populations at a given date. Now, 75 years from here, obviously, I'm not going to be here. Okay? 13, yeah, I might. My dad will be 99 in 2 weeks. He still lives alone in his home. So, yeah, I've got the genes to last a little while. All right, here we go. Now we're switching to something else. We're making a switch now. We're dealing with exponential equations, and we're going to try to solve some simple ones. I'm going to get out of my calculator and go back into the PowerPoint of this, which shows things sequentially a little more now. Okay. Got an equal sign with stuff on both sides. Now we're talking about equations for a change. Not before. And here is another one. They're just simply called exponential equations because they've got an exponential value in it. Okay, now these are just some rules about this, that A has to be bigger than 0 and A can't be 1, because if it's 1 it doesn't mean anything, and if it's 0 it's 0. Okay, so let's go to this. Here's how you solve this problem. This one's kind of a mental challenge on this one, okay? And it's easy. You've got this equation right here. You've got a base of 5. Okay? Now, here's the trick. This number, 125, is also 5 to the 3rd. Okay? 5, 25, 125. Another reason why you guys need to be spending time learning those things on my exponents handout. Okay? So now this equation is written this way. When I've got the same base, I can just take the exponents, write that as an equation, and solve what the answer is. What's my most famous rule of every rule we've had this semester? Do it to both sides, right? Subtract both sides, add both sides, square root both sides, power both sides, you know. But everything is both sides when it's dealing with equations. Well, in this case, we're removing the base on both sides. And later on, we're going to insert a base on both sides. Okay, but the trick is both sides. So anyway, here we go. Solve this, you get x equals 3. Let's see it. Here's the check already. We're going to replace the x with a 3. Okay, 2 times 3 is 6 minus 3 is 3. And 5 to the 3rd is indeed 125. So it checks out. So this is your first line of how to solve exponential equations. And this is a method that we'll use in a number of cases. Okay, now, what about this one? 4 is the power of 2, 8 is the power of 2. So we can modify this thing. What can we modify it to? Well, we can change 1/4 to 2 to the negative 2nd. There's kind of an interim step in there. We've got 1 over 2 to the 2nd like that. Convert this to that, and then convert that to this. Okay? What about this one? Well, 8 is 2 to the 3rd, 2 times 2 times 2. And then we still got this x out here. Well, we're going to use the power rule on these two now. So we now have this equals that. What's coming next? Pull the bases. Okay, pull the bases. Both sides. And we get a simple equation. And we solve it. And we get x equals negative 2/3. Well, you can actually put a negative 2/3 in there and prove that that is correct. Cube root of 8 is 2, squared is negative squared is 1/4. Okay, what about this one? Power of 2, power of 2. So we can convert it. This is equal to 2 to the third to the x plus 3 power. That one's equal to 2 to the second to the 5 minus 2x power. So now we're going to distribute that power right there. All we did right here is we just put these in parentheses so far. I would have done it instead of writing that top line. Would have done it from the beginning. 3 times x is 3x. There's a missing step in here. Okay, that missing step is 2 to the 3x plus 9 power and 2 to the 10 minus 4x power. That's a missing step in here. Maybe it fills in a gap how I went from this to this. And then they pulled the 2's to get this step. Okay, what are we going to do now? Well, we're going to get the variables on one side, the numbers on the other by adding opposites. And when we do that, we end up with this. I don't think I need to go with the minus 9 and plus 4x plus. Okay, so we get that. We divide both sides by 7, and we get an answer of 1/7. Any questions how we did this problem? Okay. Yeah, it's not time to kill you. I almost let you guys go accidentally early, like I did that one time before. Don't want to make that same mistake twice. You're thinking, oh, shucks. Okay, power of 5, power of 5. We got that. Probably ought to put this in parentheses. We're going to pull the 5's and solve the equation. Starting to get kind of repetitive and simple, isn't it? Okay, it's just different numbers every time. Let's go to something better. Logarithmic. Now, logarithms by their very nature are inverses. Okay, they are inverses of some equation, some exponential equation, to be more specific. You don't need to write all of them. These are just the things we're going to do. You need to write that down. It's one at a time. If these are real numbers, b is not 1, then this is called the logarithmic function with b as base, and this is equivalent to that. Okay, this is equivalent to that. Now I'm going to show you how to convert between those two forms in just a little bit, but there's something else that I need to tell you first. I said a moment ago that logarithms are inverses. If this logarithm means the same thing as that, what we've been doing so far is that, but we've been doing equals b to the x. That's what we've been doing up to this point for our exponentials. Okay, what did we do here? We have interchanged the location of the x's and y's. Okay, so what that means then is this stuff we've been doing Now we're dealing with its inverse, which can be shown either this way or it can be shown that way. So that's what we're ultimately doing in this. So we're dealing with inverses, and remember, when you graph inverses, they reflect across that 45-degree line. Okay, so let's go on. And here I'm just kind of talking about this. This is some language. When you look at this format right here, what this is saying, y is called the logarithm, or the log, b is the base, and x is called the argument. Okay? Over here, the argument is equal to the base to the logarithm power. And then here I'm just reminding you what I already wrote in red up there a moment ago. Okay, now, what about this? Log of -1. By the way, there's a hidden y out here, if it's not shown. This is undefined. Okay? This argument cannot be negative. Cannot be negative. And there's no solution if you have that. And it doesn't matter what the base is. If that's a negative value there, won't go. Undefined. Okay? All right. Let's rewrite this one in exponential form. Log base 2 of, notice how I'm is log, you can say log base 2 of 32 equals 5, or you can just simply say log 2 of 32, 5. Now, I want to show you what this thing means. When you see this, you think 2 to what power equals 32? 2 to what power equals 32? 2, 4, 8, 16, 32, fifth power. See, we can figure this out without a calculator. If I didn't give you that 5. Because here's how you think about this. Whatever this is, to what power equals that? So that's the mindset I want you to be in on these. Well, correspondingly, that is a true statement. Now, how do we go from this to that statement? Notice the base stays the same. First step, base stays the same. The logarithm becomes the power. And if we didn't know this, okay, then the argument becomes the answer. So 2 to the y equals 2. Well, it's going to be fifth power. And that's your way of thinking about these things. So here's just kind of illustrating what goes where. The base always stays the same. The argument becomes the power, the log becomes the power, and the argument becomes the answer. What about this one? Is that true? Is that true? 10 to what power is 1,000th. As I spit. Well, what are the powers of fractions? 1/10, 100th, 1,000th. Third basement power. This thing right here could be rewritten as 10 to the third down here. Okay. So if I had 1/10 to the third, that in turn could be written as 10 to the negative third. Agreed? So I could rewrite this problem as log 10 of 10 to the negative third equals don't know. Okay. Well, 10 to what power makes this? Well, it's going to be -3. And if all we're doing is converting it, what I did over here is I just proved that it was -3. That's all I was doing over here. Now we're going to convert it into the other format. Base stays the same. Here's your power. Here's your argument. Okay? It's always the same. You look a little unsure.
Okay, so why is that -3 not under? I thought all of the negatives was supposed to be under.
It was a power, not a number. That makes the difference. To answer what's your question, I said this could be replaced with 10 to the -3. That is not the same as -10 to the -3. That one would be undefined. But this one is okay. Because there is a positive in that. This is still a positive fraction. Did that answer your question?
Yeah.
Okay. All right, what about this one? Well, let's convert it. Base stays the same, power, argument. To the 0 power 1. Yeah, so it works. Okay, about the 2 to 16. 2 to what power is 16? There is a hidden in every one of these equals y. What is y? And we're solving for y, because now we're not putting the number out here. So they're asking us to do that. 10 to what, or 2 to what power is 16? 2, 4, 8, 16, 4. Answer is 4. Okay? And likewise, 2 to the 4th equals 16 when you convert it to exponential. Okay? What about this one? 16 to the power equals 4. Isn't the square root of 16 equal to 4? And what power is a square root? A square root is a half power. Okay, if you converted a radical to a fraction. So, in this case, down here on C, okay, you get 1/2 for the power. Okay. Now, Can you put that in your calculator? Can you put this in your calculator? Yes. Let's do that. Now I'm going to show you why these Casios are so much better than anything else. Okay, I'm going to put in log 16 of 4. Okay, see this key right up here that I'm pointing at with my arrow? This log anything of anything. I'm going to hit that key. And I'm going to put in the 16. 1, 6. And then I'm going to scroll over to that, and I'm going to put the 4. And then I'm going to hit equals. That key right up there, log anything of anything, is a key that TIs don't have. Okay? It's also a key that when we start doing change of base will save you 4 manual steps. So that's why I encourage you to use this particular type of calculators. Okay? Well, if we look at problem B, 10 to what power is 1,000? 10 100,000, so it's 3. Likewise, 10 to the third equals 1,000 for the check. This one, 10 to 0, getting tricky here. You know what? This is the same problem as we had before when we had over 1,000. Because that is 1,000. So what's the answer going to be? In this case, -3. And 10 to the negative third is 0.123 digits behind the decimal. Okay? Oh, I'm out of. Okay, here's some more. These are rules. You've got these in those 4 pages from 17 to 20. Okay? They may be handy to keep out when you're doing ALEX. Now, based on those rules, these are kind of equivalent to some of the rules, and actually pages that I got is showing you the equivalence of log rules with just standard exponent rules. Okay? Now, anytime you got a 1 here, the answer is going to be a 0. What to anything to what power is going to be equal to 1? Well, 5 to the 0 is 1. 9 to the 0 is 1. Okay? Because you're really thinking on this problem is you're thinking a to the 0 power equals 1. And whatever you substitute for a is going to still equal 1. And that's what this one is saying. Okay? Over here, here's another rule. A of a equals 1. Well, let's put this in exponential. A to the first equals itself. Is it equivalent? A to the first power is itself. So therefore, anytime you see an A of A, a B of B, a Q of Q in logarithm, it's going to be equal to 1. So these are 2 major problem-solving rules that we're headed towards. Okay? This is just saying that logarithms are exponents, okay? And I've already shown you that up here. And here, a couple of examples. Again, we're just converting here. we're using e to the w equals this, so log of this equals that. But log base e can also be written as just ln, to answer your question before. Okay, so if you have log base e, you can just hit the ln key and it automatically includes it. The rest of this, as you see, is the same. And with that, we're out of time today. So have a good weekend. Now,